Hello, this is a review of linked lists for CS330. Now the purpose of this review is to both review 150-250 material, meaning 150-250 code and mechanics and techniques you learned in those courses, and move into the CS330 material, the big three, copy constructors, the destructor, assignment operator, best practices with constant correctness, basically putting together everything you learned in CS 150 and CS 250 and reviewing it a little bit. Now on my screen right now I have a makefile. I'm going to go ahead and jump into the example. Now when you download the zip file review1.zip and extract it, you will have three items: example 1, example 2, and example 3. The other two items you see on my screen, deploy.sh, a shell script, and the zip file, will not be present when you extract it. Those are items I use to prepare the example so that you can use them. Now within each example you will find four items: documentation, which is the web-based documentation if you'd like to take a look at the code in a little slightly different form; source, which is the code itself along with the makefile; documentation.config. This is the configuration file I use to generate the documentation. I'm including it for your interest, but you will not need to make use of it. Simply including it for your interest. Documentation.htm is a basic HTML file that will open up the web-based documentation I've provided in your web browser of choice, which hopefully isn't anything based on Internet Explorer or Edge, but it will open up in whatever your default web browser is, which is hopefully a good web browser that's not Internet Explorer. Now, a couple things before we get started. I have adjusted the volume on my microphone based on some feedback I got about the orientation. It was indicated that my microphone was set a little bit low there. So if you'd like me to adjust the volume in future recordings, go ahead and shoot me an email or make a post on the discussion board indicating such. Now, what I have up on my screen right now is the makefile from example 1. Now, you should have been forced to use makefiles in CS250, and you were required to go through the makefile exercises in CS252. Now, being able to write a makefile is a very, very good skill to have. However, you do not need to be able to write a makefile from scratch in this course. You simply need to be able to use one that's been provided to you. Now, as you can see here, this is a very basic makefile, very quick and dirty. You'll see with the assignments I provide a little bit more complete makefiles, a little bit more robust. However, this one gets the job done, so this is the one I'll be using for most of my examples this semester, with a few modifications as each example changes a little bit. Now, a quick note: all of my code makes use of C++11 features, which is something you should be familiar with having taken CS250 here. Make sure you have enabled the C++11 standard in your IDE of choice within the compiler settings. In code blocks, that's underneath project preferences, compiler settings. In Eclipse, it's somewhere similar. But make sure you have done that. If you get any compilation warnings for these examples, make sure you've enabled that compilation flag. That will be the issue. Now you can go ahead and extract these under your CS accounts on the Linux servers and use the makefiles directly there, or under Cygwin or a bash shell, or on your Linux or OS X machines if you're running a Mac. Now, as far as makefiles go and what I expect you to be able to do, I expect you to be able to type make clean, and be able to run a program at the command line, like so. If you can do those three things, that's all you need to be able to do with a makefile. Use one that's been provided to you, type make, be able to type make clean, and you're good. Now I'm going to start off at a little bit of a higher level than I normally do, meaning in the top-down perspective. I'm going to start at the very, very top of the example and work down to the lower levels, the lower level implementation. So the first thing I'm going to start with is command line arguments. Now, command line arguments are not running a program being prompted to enter a value, entering that value and pressing enter. Command line arguments are arguments you supply when you invoke the program, when you run the executable immediately. Now, in this case, the executable LL2, which is the name of the linked list example executable, can accept no command line arguments, one command line argument, or two command line arguments. Now, assignment 1 does require you to use command line arguments, and in fact, you will get an error message if you have not configured your IDE to supply those command line arguments. Now, every program that accepts command line arguments requires them for different reasons, or they may be optional. In this case, for this example, the command line arguments are optional, but in assignment 1, they are mandatory. You must supply them, otherwise you will get an error message. Here, in this example, the linked list example I'm discussing right now, the command line arguments specify two things. The first command line argument, let's say 10, is a seed to the random number generator. Now, anytime you're testing a program, you would like to be able to reproduce the output. Now, by supplying an explicit seed to the random number generator, you can force it to generate the same sequence of random numbers each time it is run. The second argument, the 4 I am typing here, is the number of nodes I want to add to the linked list. In this case, I want a linked list. I want to add 4 integers and store them in that linked list. Go ahead and do that. Now, how are command line arguments implemented? How do I write a program to make use of those? That is in listdriver.cpp, and you can see that I initially developed this example last semester in the fall based on a CS250, meaning a CS333 example from a couple semesters prior. Now, there are two files I am glossing over, utilities.h and utilities.cpp. Those are two files with some functions I commonly use for generating the headings and dividing lines, basically making the output look pretty. There is really nothing of consequence there. If you're interested, you can go ahead and take a look at them, but there's really nothing special about them, just some common heading functions, dividing line functions, and maybe a couple other functions I found myself writing quite frequently. Listdriver.cpp is where we will start. Now, we should all recognize our include preprocessor directives for built-in libraries. We should also recognize include preprocessor directives for header files I have written. Now, as you can see here, I have included header files. Header files are the only things you include using include. You should never include a CPP file. Once again, something that should have been taught very, very heavily in CS250. We can see using namespace standard and using namespace utilities. Where using namespace standard is the line you have been writing since CS150, and using namespace utilities is a namespace I created for all the utilities I commonly use. Next, we should recognize that we have a number of constant variables, global constants. We can tell that by the naming convention used, all caps with underscores to divide words. Program heading is a constant array that I use to generate the heading. Heading lines is the number of lines in that heading. And min and max are the default ranges for the random number generation, meaning by default I will generate numbers in the range -10 to 10. We see a forward declaration for the random int function, forward declaration alternatively called a function header, function prototype. And we can see I am making use of default argument values, meaning by default, if I do not supply min and max values, it will default to those constants. We see my standard main function int main, int argc, argv for accepting command line arguments. Once again, something you saw in CS250, something I'm forcing you to review now. we see a pointer to a linked list object, random ints. And we're initializing it to null pointer as opposed to the more commonly taught null, capital N, capital U, capital L, capital L. Null pointer is something added in the C++11 standard. It is something that is guaranteed to always be a pointer value as opposed to null, which can be downcast into 0 and introduce a number of errors. So in all my examples, you will see me use null pointer over the more traditional null. Null pointer is what you should favor. You should use null pointer over null all the time. You can see I declare two more integers, seed and toGenerate, where seed is what I'm going to use to capture the seed to the random number generator, and toGenerate will capture the number of nodes I want to add to my linked list, meaning the number of random integers I wish to generate. We can see that the first step, because I'm working with command line arguments, is to check the number of command line arguments. Now, going back, we can see that in this case, I have 2 command line arguments that I type, but I really have 3. The first command line argument, by virtue of how command line arguments work, is the name of the executable itself. /ll2 is the first command line argument, followed by the command line argument I type, and then the next one. So even though I specified 2 command line arguments, because the executable itself is included, I really have 3. So if I have 2 command line arguments, that means I have specified a seed to the random number generator, if I have at least 2. What I'm going to do is I'm going to use the old school character string to integer conversion function, something you should have seen in the past, but convert a C style string to an integer. The first argument I specify, meaning skip over the executable, grab that first number I entered. If I do not specify a seed to the random number generator, default to time, as you have seen in the past. Then, if I've specified 3 command line arguments, meaning the executable, a seed to the random number generator, and the number of integers I want to generate, grab the second command line argument I specified, in practice the third, convert it to an integer from a C style string. Otherwise, if I did not specify such a command line argument, default to 10 nodes, default to generating 10 integers. Once I have done all that, then I seed the random number generator. Then, further down, I print the project heading using one of my utility functions. Then I create a new linked list object, explicitly invoking the default constructor using the pointer I allocated earlier. I then have a for loop that will, starting at using int I equals 0, will add a new random integer, will append a new node to my linked list until I have generated the number of nodes I specified. Now we know based on this that append node is a member function of this linked list class I have defined, and I know that it is referenced via a pointer to a linked list called random ints. And we can see that I am generating a random integer by calling the random int function, and because I have specified no arguments to that function, it's defaulting to the default min-max constants. We can then see later on that I output the linked list using a standard cout statement. We can see that first I grab my random ints pointer, a pointer to a linked list, dereference that pointer to get direct access to the linked list, and then output it using a standard stream insertion operation, a standard output operation. Now we know based on our experience in CS250 with operator overloading that I have defined the stream insertion operator. Now the stream insertion operator is the proper name for the output operator cout operator. The more or less colloquially used names, the commonly used names as taught in CS250. The proper name for the output operator is the stream insertion operator. You're inserting into the output stream. I then print a horizontal dividing line using one of my utilities functions. Now, I need to clean up after myself. I need to delete the linked list object, so I'm going to take that pointer, I'm going to call the delete operation. I then get down to return 0 in my main function, and I know, based On what I was taught in CS150, CS250, I always need to include this line in my main function. Now, one of the things that's sort of glossed over is why it's returned 0. Anytime you reach the end of execution of your main function without issue, you should always return 0. 0 indicates that your program ran to completion without issue. If we scroll up, we see that there are no other returns. So we can see that this program should always run to completion without issue. And we'll see in later examples this semester, I have non-zero return values at different points when I'm looking for errors in input. If we scroll down, we can see a very, very basic random integer generation function. This is a very old function. This is a function I've written a number of times to demonstrate the basic use of the srand and rand functions. There are more elegant ways of generating random floating point values. For example, the different distribution functions supplied by C++11, the uniform, rand, and all of that. This is a very, very introductory level approach, a very basic approach using the basic rand function. Basically what I'm doing here is I'm generating a random integer and multiplying it by 1.0. By multiplying an integer 1.0 by 1.0, I end up with that integer represented as a floating point value, meaning I end up with a double. I then divide that double by an integer, the maximum possible random number, meaning rand max, a built-in constant. I then have a number between 0 and 1. I then take the max and min values, in our case 10 minus negative 10, which gives me a value of 20. I add 1 to get a value of 21, and that is my scaling factor. So I'm going to take that number between 0 and 1 and multiply it by 21 in this case, which is what you see here. Take the random floating point value between 0 and 1 I generated, multiply it by my scaling factor, which is 21, and offset that by the minimum, meaning this first step here will give me a number between 0 and 21. I don't want a number between 0 and 21. I want a number between negative 10 and 10. So add negative 10 to that. That turns a value that's between 0 and 21 to a value that's between negative 10 and 11, where 11 is an upper bound, which will be truncated off, right? So I'll end up with a number between negative 10 and 10. Very basic function, a very inelegant function. Not one on which I will evaluate you, but one that's good to know if you're in a language that doesn't have a nice random number generation utility in place. Now, as you can see, I've talked about an append node function and a linked list. We've written an append node function many times in previous courses, but you can see I took a top-down approach. I'm assuming that somebody entering a 300 level course can look at this code and say, okay, random int is a pointer to a linked list object. Okay, that's a class I defined in linklist.h and linklist.cpp compiled, and I'm using here. Append node is a member function. I'm also assuming that somebody who has reached this point is familiar with saying, oh, okay, this indicates that an operator has been overloaded for stream insertion somewhere. I don't expect at this point anybody to, based on the code I've shown you just now, say, oh, this is how it's implemented. I'm simply looking for you to understand that this is an interface that has been provided. This interface has been implemented in some way. This interface is the focal point. Append node and stream insertion, constructor, destructor, all of that. I simply need to recognize that these methods, these member functions and functions have been implemented. Now, to get down into the implementation, we can see my standard if and def defined. These are what are referred to as compiler guards, meaning this if and def node h included, define node h included, and end if prevent the header file from being included multiple times. Basically, what those guard against is something like this. I can include node.h as many times as I want, and because of these two lines here and this line down here, the rest of these includes will be ignored. Now, of course, Even though that won't be an issue, it makes the code very, very difficult to read, so I'm going to go ahead and remove those lines. But if you add them back in, you'll see that those compiler guards prevent it from being an issue. They'll ignore the duplicate includes within this file. Now, we can see a node very, very similar to what you saw in CS250 or an equivalent course. I have a linked list node, meaning a node I use to build a linked list. In this case, I have some integer piece of data. Maybe in a more developed version of a linked list, I'm using a book object, meaning I'm going to store book object or something else. Or maybe I even develop it further and I use a template function and say, this is a, well, templates, and I say, this is a node of template type T. I have some generic type T data. But in this case, to keep it simple, to avoid all that, I'm going to just say data is an integer. But I could change it to a string, a character, a data type I define, it doesn't matter. But in this case, I'm going to stick with integers. I then have a pointer to another node. Now, I have called it next here because I know I will be using this to build a linked list, but it's just a pointer to another node that happens to be the next node in the linked list. If there is not another node after this, it points to null. We can see a default constructor, a non-default constructor that accepts an integer, a logical equivalence operator, and a not equals operator. And we can see in this example, I am violating the C++ class checklist. But once again, this is taking a step back to the end of CS250. And we see here that this is node.h, this is a header file, it contains only declarations. Header files contain only declarations. Once again, a very big point that should have been taught in CS250 and emphasized very, very, very heavily. I then have my definitions in a CPP file. In the case of node, node.cpp. And we can see I define the default constructor here. And we can see that for some reason I have extra space and that should not be there. There we go. We have a default constructor for node. Once again, the node default constructor within the scope of the node class. Standard scope resolution operator, standard syntax you saw in CS250. I'm initializing data to 0 and next to null. I'm initializing them to appropriate 0 values that I, the programmer, have defined. I have my non-default constructor that takes a piece of integer data, initializes the data attribute of my node to that piece of data, initializes the next pointer to null. I have my logical equivalence operator that is responsible for saying, is this node the same as another node? I am defining that for two nodes to be equivalent, both their data and the node they reference as the next node must be the same. That is how I define two nodes as being the same. Then I have the not equals operator. For nodes to be different, I just need one of those to be true. For two nodes to be different, I need for either the data to be different or the next pointer to be different. If one of those is different, they're different. And there are some tricks I can use to get the compiler to build the rest of the comparison functions for me, but that's a discussion for later in the course. But a very basic node implementation, something we should have seen in CS250. Now we get into the linked list. This is where the fun begins. Now, when I build a linked list, in general, all I need is a pointer to the beginning of my list. That is it. That is all I need for a very, very basic, rough implementation. However, anytime I personally implement a linked list, I always include three things. Well, usually include three things. A head pointer, a tail pointer, and a node counter. The head pointer points to the beginning of my list. The tail pointer points to the end of my list. And the node counter is an integer counter that I maintain so I can keep track of the number of nodes in my list. So I can immediately find out how many nodes are in my list without doing any work, without a loop. And we can see it needs node.h, so it includes node.h. We can see my private member data, the head pointer, the pointer to a node, the tail pointer, the pointer to another node, where head is the beginning of my list and tail is the last item in my linked list. I have the integer counter for the number of nodes. I have a default constructor, a destructor, a prepend node function to add a node to the beginning of the list, an append node to add a node to the end of the list. Now, I've included both of these functions for completeness. However, in your first assignment, you will only need to do an append operation. So I'm going to go ahead and skip over prepend node and focus the discussion on the append node function. So the prepend node is included for completeness, and for your interest, if you'd like to discuss it in more detail, I'd be happy to do so during my office hours, but I'm going to focus on the append node function. I then get down to the size function here, which is defined as const. This indicates the trailing const, as you learned in CS250, indicates that this is a read-only function, meaning within this function I only examine values. I make no changes to the linked list or any of the attributes. I make no change to the state of my linked list. Then I have my display function. This is a very common way of writing a display function, something you should recall from CS250. And once again, this is a display function. It is a read-only operation. It does not modify the linked list. I am passing in an output stream. And once again, as you should recall from CS250, this allows me to pass in any arbitrary output stream. Cout, cerr, an output file stream, or an output string stream, or anything that implements that OStream interface. I then have a function definition violating a rule I indicated earlier. Now you'll note the keyword inline. An inline function is a function that you write as if you're writing a normal function, but you declare it as inline. This is a hint to the compiler to indicate that when the compiler is going through your code and building the executable code that the processor will later run, to take the code you have written here and pretend as if you had written the corresponding statements inline. Basically, it is an optimization hint. It's basically hinting to the compiler that this is a good piece of code to optimize. Instead of, even though I've written this as a function, go ahead and rework my code as you're going through it so that it is not compiled into the function. It's compiled as code inline where the function is called. And once again, there are a number of notes in that from CS250 and CS333, another topic that you should recall from there. But once again, all we're doing is we're gathering all of these techniques, topics, keywords, mechanics from CS250, putting them all together and make sure we remember all of them, and we're making use of them according to best practices. Where many of those practices are still being violated from this example, but we're putting together some of them right now. I then get into the implementation of my linked list, linkedlist.cpp. Once again, default constructor. When I first create a linked list, it's empty. And if I have an empty linked list, the head and tail pointers don't point anywhere. There are no nodes in my list, meaning I have exactly 0 nodes. I have a destructor for a linked list. I need to go through my linked list and disassemble it. I'll come back to this in a moment. I have the prepend node function, which adds a node to the beginning of the list. I'm going to go ahead and skip that as well. I have the append node function that adds a node to the linked list. And I have the size function. And this simply returns the node's integer counter. Now you will note this is a very simple function, and it could have been written as an inline function. Why didn't I write it as an inline function? I flipped a coin. Oh no, I didn't flip a coin. I decided not to write it as an inline function so I can make this exact statement. This is a good candidate for an inline function. Then I get down to my display function. And the reason I've jumped down to the display function is in CS250, whenever you work with linked lists, in CS150, whenever you work with linked lists, this is the most basic function you write when it comes to linked lists. Traversing a linked list, outputting the data within each node. Now, the integer index I'm using here is something I've purely added for the benefit of this discussion. It is not required for this loop. It's only required so I can get that nice integer counter. Whenever I traverse a linked list from beginning to end, I need an iterating variable. In this case, it to follow along with the naming convention used with the STL containers. The iterator needs to start at the beginning of my linked list, the head of my linked list. I'm going to write my standard linked list while loop, while the iterator is not equal to null, while I have not reached the end of my linked list. Do some stuff, then move to the next item in my linked list. Take that iterator and update it to point to the next node in the list. Now I'm working with an index, so all I'm doing is incrementing that so it outputs 1, then 2, then 3, then 4. Fine. Once again, purely something for the benefit of output. This output statement here, I've added in some formatting for the sake of this discussion. However, it simply makes it look pretty. But in assignments, it's generally 1 or 2 spaces hard-coded because formatting is hard enough. So 1 or 2 spaces generally in assignments. But looking here, I've used some formatting to make this example look pretty. We can see that I output the literal string node number and a space, and then the index. Then I output a space, a dash, a space, and then the actual random integer I generated and stored in the list. And then I end the line with a line feed. Now, when you're working on your first assignment, maybe you don't need to output all of this explicitly. Maybe if you're careful, the data stored in your linked list has some sort of stream insertion operator defined elsewhere. It is very important that you understand all of the interfaces at play and how they interact before you write a line of code. You must understand what code you're using, where it is. And now we can jump all the way back up to the append node function. Now we can see this is your standard append node function code, and we can see I've documented it quite heavily here. Anytime you want to add a new node to a linked list, you must first get the data. In this case, I've called the data to add. You must construct a new node, which is what I've done here. I've constructed a pointer that will reference this new node. I then explicitly construct a new node. Take that new node pointer and create a new node invoking the second constructor, invoking the constructor that takes a piece of data as input, initializes that data, and sets next to null pointer. I then say, what are my special cases for a linked list? And I really only have one special case, when the first node in my linked list is added. When I am adding my first node to my linked list, I am going from an empty list to a non-empty list. So what I need to do is I need to check, is my linked list currently empty? Is this the first node I am adding to my linked list? If it is, I need to treat it specially. I'm going to take that new node and add it to the beginning of my list, meaning the head pointer, the node that points to my beginning of my list, needs to point to that node. However, if I'm adding the first node, I have a linked list with exactly one node. So that first node is also my last node. I've added my first node. I need to increment my counter. And I am making sure that that new node pointer I used won't be used mistakenly by me elsewhere. Line 123 isn't necessary mechanically. It's something I include because if I don't, I know I will make a mistake later. It's one of those stylistic things you pick up to prevent yourself from making mistakes. Now pretend I'm calling this function for the second or third or fifth or 18th time. I'm going to go through, create a new node again. I'm going to check, am I adding the first node? No, I'm adding the second, the third, the 8th, the 15th. Okay, so now that I know that this is not my first node, I need to add it after my current last node. Meaning, if I'm adding a new node to the end of my list, I need to first go to the end of my list, this tail. Once I have grabbed a pointer to that last node, I need to go within my last node and grab the next pointer within that last node. So step 1, grab the last node. Step 2, grab the next pointer within that last node and have it point to that new node I just created. Now, anytime I add a new node to the end of my list, I must update my tail pointer. Now, the fact that the head pointer must always point to the beginning of my linked list and the tail pointer must always point to the end of my linked list, those are what are referred to as post conditions. In this case, undocumented post conditions. When this function returns, I am guaranteed that the head pointer will point to the beginning of my list and the tail pointer will point to the end of my list. Once again, that is what is referred to as a post condition. When I call append node as an undocumented precondition, I am guaranteed that the head pointer and tail pointer and count have been initialized appropriately and hold correct values. Once again, an undocumented precondition and an undocumented postcondition. Two terms you should recall from CS250. And now that we've done the fairly straightforward functions, meaning the first two linked list functions you were taught in 150, now we can get to the more fun one, the destructor for our linked list. Now, I've been very verbose in how I wrote this method. I have written in such a way that I'm using multiple pointers to make explanation easier. However, there are many ways to write this function. It can be written using fewer pointers, but this is the most straightforward way for the sake of discussion. I declare two pointers in the beginning. This iterator, this is going to be the pointer that moves through my linked list starting at the first node, going all the way through to the end. Then I have a toDelete pointer. This is the pointer I'm going to use to delete a node. So I'm going to start with my standard linked list while loop. I need my iterator to point to the beginning of my list. I then want to traverse my list until I have reached the end. The first step is going to be, I want to delete the current node. I have my iterator, it's referencing a node, I want to delete that node. So I'm going to set toDelete appropriately. But before I delete the current node, I must move my iterator to the next node. So all we've really done here is move the step earlier in the loop as opposed to the end. As soon as I have moved my iterator forward one, I can delete the now previous node. I'm then going to set toDelete to null. Now, in this case, once again, I do not need to set toDelete to null because I will be immediately resetting it in the next loop iteration. However, I have done so explicitly here to prevent myself from making a silly mistake if I do any sort of debugging output or modifications later. I then get down to line 39. This is a line I've included for the purposes of debugging and for discussion. In a complete linked list implementation that were non-academic in nature, I would not include this line. Now this is debugging output, so I'm not going to write to standard out, I'm going to write to standard error. Standard error is represented in C++ by the C error output stream. Once again, writing to C error for debugging, another topic from CS250 in the debugging module towards the end of the course, and for module 3 in CS333. I have then disassembled my list. I'm going to reset my head pointer to null, my tail pointer to null, and my node counter to 0. Once again, these last three assignments are not necessary because they're in the destructor. However, I have written them to prevent myself from making a silly mistake later. You can see with that, all I really have here is my standard linked list code from CS 150 and 250 reorganized. This is code I've written before, mechanics I've employed before. All I've done is put them together and reorganize them. Let's take one last look at the results of running this code. Now, what I would like to do is I would like to capture this output in a text file. So I'm going to take a step back and review something you discussed in CS252 and CS250. In CS250, this was in the head-to-head testing portion of the course. What I'm going to do here is I want to dump this to a text file. So what I am going to do is say output redirection ex1.txt. And we can see that when I check that text file, it does not include the deleted node lines. It's not including those lines. When you do output redirection with just the greater than error here, it defaults to only doing standard output. It discards standard error output. Now you can do this slightly differently to catch that as well, but I only want what was written to standard out. I don't want my debugging code in here. So I'm going to stick with just this output here. And now I'm going to jump into example 2. Now I'm just going to go ahead and run those 3 commands immediately. And I'm going to run example 2. Now one thing you will notice is the name of the executable for example 2 is the same. All I've done in example 2 is reorganize the node and linked list code slightly. And I'll get to that in a moment. But if I run the second example, I notice it looks very similar to the first example. But once again, I'm doing that visually. I would like to be a little bit more sure of myself. So what I am going to do is I'm going to dump this output to a text file as well. And what I would like to do is compare the 2 pieces of output. Compare the first piece of redirected output to the one I have right now. Now, looking at it with diff, they look the same, but they look like they're the same. But let's take a look with sdiff so we can see a side-by-side comparison. I do need to zoom out slightly for that one. I do need to zoom out a little bit more. There we go. And we can see that the output is in fact the same. Now what I'm going to do is I'm going to pretend the output is different by modifying this text file. So let's say that this were +6. And I did something like that. If I look at this carefully, I see that these lines here differ because of the pipe character sdiff has printed. And if I look at them with diff, I'll see something similar. It will show the lines that differ, or sdiff will show them side by side so I can actually compare them visually. Now it's very useful when working on any piece of code if you have a known good working version of the program, similar to the compiled versions of my solutions I provide. If you take that output, dump it to a text file, take the output of your program, dump it to a text file, and perform a head-to-head comparison. Perform some head-to-head testing for given sets of input, comparing the known working version of a program that gives you correct output to another version of the same of a program that should give you the same output. Head-to-head testing. Very simple, mechanically. I expect you to employ it. Very important skill, something that's very important in CS250 and something that's even more important in general in the process of testing. Now, example 2 is changed in one way. No, it does not open Chrome. That's me clicking the wrong button. If I go to example 2, you will notice that I have gotten rid of node.h and node.cpp, and I've moved those into linklist.h and linklist.cpp respectively. What I've done here is I've said this node structure I have defined is used only to implement a linked list. It is an implementation detail. Conceptually, a node only exists within the scope of a linked list. So what I'm saying now is, within my linked list, a node is private. What that means is, while the structure exists, it can only be used in instances, meaning node objects can only exist within a linked list. No outside code is aware this exists. A good example of this is the list container from the standard template library and the forward list container from the standard template libraries. They have some sort of internal data structure that you use to implement the list, but you never work with it directly. It is hidden from you. Whenever you want to traverse that list, you make use of an iterator, which hides the implementation details. So all I've done is move that very same node code within the scope of the linked list. The rest of the linked list code is the same. The rest of the node code is the same. Now we get to the line that throws a number of students off oftentimes, and that is this line here. Linked list node. Now if I remove this portion of the line, you'll say, yep, makes sense, not a problem. All this means is I am defining the node constructor for the node class, and the node class itself exists within the scope of the linked list class. It's simply another level of scope. And we'll see that for every node member function, it's defined within the scope of the node class, and the node class is itself defined within the scope of the linked list class. But beyond that, the rest of the code here is the same. And that's example 2. One small change. Then we get to example 3. And this is where I finally start honoring the rule of the big 3. Now, the rule of the big 3 states if you implement one of the big 3, you implement all of the big 3. Now, the big 3 are in order: copy constructor, destructor, assignment operator. Now, in the past, you have not needed to implement these because you were performing shallow copies, meaning working with integers, doubles, strings, things that provided default constructors or basic value types. You were not working with memory directly. Here we are working with pointers. I don't want to perform shallow copies on these pointers if I create a copy of a linked list. I want to perform deep copies. I want to copy the data itself and create a separate yet identical linked list. So the node code is once again the same. The default constructor is the same. I now introduce the copy constructor. I still have the default destructor. And now I've introduced the assignment operator. So I only have 2 new functions here: a destructor and the assignment operator. Excuse me, a copy constructor and the assignment operator. I inherited the destructor from the previous 2 examples. Now, if I jump down to the copy constructor, we'll see it's a standard constructor at its core. I have basically taken the default constructor code and started with that. Now, a rule that is glossed over in CS250 is every constructor must initialize every data member, meaning by the time a constructor finishes, every piece of private member data, public data member, or protected member data must be initialized. Now, in the case of integers, pointers, and characters, you must do that explicitly. If you're working with a string or a type that is a class, their default constructors will be invoked implicitly through what's called an initializer list, which I'll discuss in a set of examples in the next review. But by the time your constructor finishes, you need to be able to guarantee that every piece of data within your class, every piece of member data has been initialized. And that's what these 3 lines do. Now, as its name suggests, the copy constructor copies another object. So in this case, I want to copy into this linked list the data from some source linked list. So once again, I'm going to introduce an iterator. I'm going to call this source iterator. I am going to set it equal to the head pointer of the source linked list. I am then going to traverse the source linked list until I have traversed the entirety of the source linked list, and I'm going to perform that iterating step. This is where it gets fun. What I want to do is I want to extract the data from each node in my source linked list. I want to take that extracted data and append a new node containing that source data to this new linked list. I want to copy the data from the source node within the source linked list into a new node I am appending to this linked list. Now, assuming my append node function has been written correctly, why not reuse it here? Code reuse. I'm appending nodes to a new linked list. I've written a function that does just that. The only difference is I am first grabbing that data from a source node in a source linked list. The destructor code is the same. And then I get down to the assignment operator. Now, if I look at this, I will see that the lines I have highlighted are my destructor code copied and pasted. I have copied and pasted my destructor code. Then immediately after that, I have copied and pasted my copy constructor code, where these 3 lines overlap between the 2. Now, anytime I write an assignment operator, I must wrap all of the codes that make the code that makes changes within this conditional block. If this not equal to ampersand right hand side. This is a pointer to the current linked list object. Right hand side is a linked list object I have passed by reference. The ampersand on line 224 is the address of operator. What this is doing is it's taking the right hand side variable and getting the memory address. I am then comparing that memory address to the memory address of this current linked list object. If those memory addresses are the same, it is the same linked list. I want to prevent a self-assignment. What is a self-assignment? A self-assignment is exactly what I have written on line 224. Is that valid C++ code? Absolutely. Does it make sense? No, but it's valid, and I need to guard against it. If this linked list object is not the same as the one I have passed in on the right-hand side, disassemble the current linked list, and after I have disassembled it and deallocated all that data, copy in the new data from the right-hand side linked list. Now, this is a very quick and dirty way to implement an assignment operator. There is a more elegant methodology called the copy and swap method. And time permitting, I will discuss that in my next set of examples as well. But that is a discussion for another time. Now that does end my discussion of these 3 linked list examples. This has been a review of CS250, mechanics all glued together, and introducing the thought process of interfaces and all of that. and enforcing the rule of the big three: the copy constructor, destructor, and assignment operator.